In the last lecture, we were examining the flow around a gas bubble, diffusion from a gas bubble of some solute with concentration Cs at the surface and concentration C infinity far away due to forced convection, where there is a free stream velocity Vfs, which is in the minus x direction, where x is the along the upstream stagnation point of the bubble of radius r, and we had used a cylindrical coordinate system in which r was the distance, small r was the distance from the origin, and theta was the azimuthal angle. And in this case, the concentration and the velocity are independent of the meridional angle phi around the axis x. There is no variation in the third direction. Therefore, the conservation equation reduced to this particular form, where the velocity Vr and V theta were specified. Okay, if you recall that there were the velocities in the two directions, Vr and V theta were specified for us. Okay. They were a function of r and theta, and we had used an approximation where the distance from the surface was small. Therefore, I could define r star is equal to 1 plus delta star eta, okay, and expand the velocities Vr and V theta in terms of this coordinate r star and theta, and retain only the largest terms. We found that V theta, which is the velocity in the theta direction, okay, which is the velocity in the streamwise direction, V theta, was finite at the surface. So, there is a slip at the surface, and V theta was equal to minus delta eta times cos theta. I am sorry, V theta was equal to sin theta by 2. Okay. There was a slip at the surface, and V theta was equal to sin theta by 2 in the plus theta direction. Vr was 0 at the surface. Okay. It increased with eta proportional to eta itself as expected, because Vr has to be 0 due to the no penetration condition at the surface. There can be no fluid flow relative to the surface. Therefore, Vr has to decrease to 0 at the surface, and Vr increases linearly away from the surface. These two approximations were substituted into the conservation equation, as you recall, and this is the equation that resulted. Okay. So, this is the equation that resulted when we had substituted the expressions for the concentration in terms of eta and the boundary layer thickness into, as well as the components of the velocity, into the mass conservation equation. The term in blue is dependent on theta, and in order to get a similarity solution, this term has to be a constant. The value of the constant will affect the dependence of the concentration on eta, but it will not affect the dependence on concentration on the original variables r star and theta. Therefore, this constant can be set equal to 1 without loss of generality. And we had solved this equation. Okay. We had solved this equation to get a solution for the temperature profile. And this solution for the temperature profile is of the same form as the error function solution that we had obtained for the unsteady transport from a flat surface in one dimension. If you recall, in that case we had got an error function formulation. A similar solution is obtained here, and from this we get the flux at the surface. The flux at the surface here depends upon this boundary layer thickness delta star, which has to be determined by solving this blue equation over here. Okay. So, let us see how to solve that. Okay. So, the equation is Pe by 2 into delta star square cos theta plus delta star sin theta by 2 d delta star by d theta is equal to 1. Constant was set equal to 1 without loss of generality. Okay. I can rewrite this equation as Pe by 2 into delta star square cos theta plus sin theta by 4 d delta star square by d theta. This is equal to 1, and I can divide throughout by the prefactor of d delta star square by d theta to get this expression. So, this is the expression that we get for the square of the boundary layer thickness delta star square. Okay, this is the expression for delta star square. Integrating factor is e power integral 0 to theta d theta, or this is actually an antiderivative, it is not a definite integral, it is d theta 4 cos theta by sin theta. This coefficient here, exponential of the integral of that, okay, is equal to e power integral d theta of 4, I'm sorry, if I integrate this, I will get derivative of sin theta is cos theta. So, I will get e power 4 natural logarithm of sin theta. Okay. You can take the 4 out, and integral of cos theta by sin theta. If sin theta is u, then cos theta d theta is du. So, you get du by u. Integral of that is log of u, okay, which is the same as e power ln of sin of theta whole to the 4th power, okay, which is equal to sin power 4 theta. Okay, sin of theta to the 4th power is the integrating factor, okay, in this case. Delta star square is equal to c by sin power 4 theta plus 1 by sin power 4 theta integral d theta prime, okay, of 8 by Pe sin theta, okay. Okay, into, okay, sin theta prime, sin power 4 of theta prime. Okay. Substituting the integrating factor here, here and here. Constant by IF, integrating factor, plus 1 over the integrating factor, integral 0 to theta of d theta prime, okay, times the inhomogeneous term, okay, the inhomogeneous term, okay, times the integrating factor, okay, the inhomogeneous term times the integrating factor. Okay. So, this can be simplified. Take factors out. So, I will get sin cubed of theta prime. Okay. We have sin power 4 theta prime divided by sin of theta prime, which is sin cubed of theta prime. And here you can use the trigonometric identity for the cube of sin theta. Sin cubed theta is equal to 1 by 4 of 3 sin of theta minus sin of 3 theta. Okay, use that trigonometric identity here. So, this is equal to c by sine power 4 theta plus 8 by P e sine power 4 theta integral 0 to theta d theta prime 1/4 of 3 sine of theta minus sine of 3 theta. Okay. And this integral is quite easily done. Okay, you will get c by sine power 4 theta plus 2 by P e sine power 4 theta into integral of sine theta is minus cos theta. Okay. Integral of sine theta is minus cos theta. So, you will get minus 3 cos of theta plus cos of 3 theta by 3. So, this is the square of the boundary layer thickness delta star square, okay, in this particular case. This goes to infinity, it appears at both theta is equal to 0 and theta equals pi, because in both cases sin theta goes to 0. Theta is equal to 0 is the upstream stagnation point. Okay. Theta equals 0 is the location of the upstream stagnation point. Okay. And theta equals pi is the location of the downstream stagnation point. Okay. Upstream stagnation point, the flow is towards the sphere, there is diffusion coming outward. So, you would expect the boundary layer thickness to be finite at that location. Okay. At the downstream stagnation point, the velocity is downstream, the diffusion is radially outward. So, the boundary layer thickness goes to infinity there. Okay. So, therefore, the constant c has to be fixed based on the condition that the boundary layer thickness is finite at theta equal to 0. Okay. At theta equals 0, delta star square is equal to c by sine power 4 theta plus 2 by P e into sine 4 theta into cos theta. Theta is 0, so cos theta is 1. So, minus 3 plus 1 by 3. Okay. That is 8 by 3. Okay. Is equal to c by sine power 4 theta minus 16 by 3 P e times sine power 4 theta. Okay. Therefore, if the boundary layer thickness has to be finite at that location, you require that c is equal to 16 by 3 P e. And this gives us the relation for the boundary layer thickness delta star is equal to delta star square, okay, is equal to 2 by P e into 8 by 3 So, this is the expression for the boundary layer thickness, and delta star is going to be equal to root of 2 by P e 1 by sine square theta into 8 by 3 minus 3 cos theta plus cos of 3 theta by 3 whole power half. Okay, so, that is the expression for the boundary layer thickness. Okay. Okay. So, now we have to calculate the local flux and the average flux. Okay. Recall the expression for the local flux. Okay. This is the expression for the local flux. Okay. So, therefore, the local flux at r is equal to r is equal to d into Cs minus C infinity, okay, by r delta star root of 2 by pi. That is the local flux. The average flux J average is equal to 1 over the total surface area 4 pi r square times integral over phi just gives me 2 pi. So, I will get 2 pi r square, okay, sin theta d theta times j r at r is equal to r. Okay. Note that I have an integral of phi from 0 to 2 pi and of theta from 0 to pi. Integral over phi just gives me 2 pi because the flux is independent of phi. Okay. So, I will get d into Cs minus C infinity by 2 r delta star. Okay. And here I have to substitute this expression for the boundary layer thickness. Okay. Here I have to substitute this expression for the boundary layer thickness. Okay. So, I will get the whole to the half power. Okay. So, this is the final expression and I have to evaluate this integral. Once again I use the substitution sin cube theta is equal to 1 by 4 of theta minus sine of 3 theta, okay, the numerator here. Okay. I will just briefly show you how this is done. I will not go into the details. Okay. Sin cube theta, I substitute this, okay. And if I consider u is equal to 8 by 3 minus 3 cos theta plus cos of 3 theta by 3, the denominator, okay, the term within the square root in the denominator, then du will be equal to the derivative of cos theta is minus sin theta. So, I will get 3 sin theta minus sin 3 theta d theta. Okay. So, the numerator is basically 1/4 of du. Okay. So, basically I have 1/4 of du times u power half. Okay. So, I will get okay, 1/4 du by u power half, okay, where u is this function of theta, where u is this function of theta. I can do the integral, and this will turn out to be equal to d into Cs minus C infinity by 2 r root of P e by pi, okay, into 1/4. Integral of 1 over u power half is 2 times u power plus half. Integral of u power minus half is 2 times u power plus half. Okay. Okay. So, it is going to be equal to 2 into u power plus half, which is 8 by 3 minus 3 cos theta plus cos of 3 theta by 3 whole power half. Okay. this integral from 0 to pi, okay. This integral from 0 to pi. Okay. At 0 this will be identically equal to 0, and at pi this will be equal to 16, at pi this will be equal to 8 by 3 minus plus 3 minus cos theta by 3. Okay. So, this will be basically equal to 16 by 3 whole power half. Okay. So, I will get d into Cs minus C infinity by 2r root of Pe by pi, okay, into this factor of half will come here into square root of 16 by 3. Okay. Okay. So, that is the final expression for the average flux. Sherwood number is equal to average flux by d Cs minus C infinity by T by the diameter, my apologies, the diameter. Okay. You can see that the denominator here is identical to what I have over here. So, those things cancel out, okay, and I will get a factor of root of Pe by pi, okay, into this will be 2 by root 3. Okay. And this is 0.652 times the Peclet number to the half power. Okay. So, that is the final expression for the Nusselt number correlation. In this case, for a mobile interface, as I told you, where the velocity, the tangential velocity is non-zero at the surface, the correlation is 0.652 times Pe power half for a spherical bubble. If you recall, for a falling film as well, okay, we had got that the Sherwood number in this case as well, if you go back and check, when we did this calculation for a falling film as part of our discussion on similarity solutions, we had got a Peclet number to the half power. Now, why is it that we get Peclet number to the half power? Okay, so, once again I can consider a general flow field. Okay. Okay. Pass some curved object. Okay. In the limit of high Peclet number, in this case now the velocity is non-zero at the surface. Okay. In this case we have a mobile interface where the velocity is non-zero at the surface. Okay. If the Peclet number is large, then the effect of diffusion from the surface is restricted to a thin region close to the surface. Okay. Is restricted to a thin region close to the surface. If the thickness of this region is small compared to the radius of curvature of the surface, then locally a two-dimensional coordinate system can be used, where x is the streamwise direction and z is the cross stream direction, okay, at the surface, where x is the streamwise direction and z is the cross stream direction at the surface. Okay. Therefore, the velocity Vx in the x direction is going to be the surface velocity, okay, in this boundary layer, okay, which is in general a function of x. Okay, the velocity at the surface is going to be the surface velocity, which is in general a function of x. And we know that the mass conservation condition is for an incompressible fluid is that the divergence of the velocity is equal to 0. Okay. If I substitute the dependence Vs of x into this equation, I will get partial Vz by partial z is equal to minus dVs by dx, okay, which will imply that Vz is equal to minus dVx by dz, sorry, dx z plus a constant. That constant is fixed by the condition that the velocity has to be equal to 0 at z is equal to 0, because there can be no penetration perpendicular to the surface. there is a velocity tangential to the surface, but there is no velocity perpendicular to the surface at the surface itself. Okay. So, those are the expressions for the velocity. Okay. Boundary conditions: C is equal to Cs at the surface, C is equal to C infinity far away. In terms of scaled coordinates, C star is equal to 1, C star is equal to 0 far away. Okay. Thus, the convection diffusion equation Vs times partial C star by partial x plus minus dVx by dx z times partial C star by partial z is equal to d times partial square C star by partial z square. Okay. Express this in terms of the similarity variable eta. Okay. Eta is equal to z by delta x of x. Okay. Recall that partial square C by partial z square is equal to 1 by delta x square d square C . Okay. The first derivative is just 1 over delta. Okay. And the derivative with respect to x, partial C minus z by delta x square substitute into the governing equation. Okay. Tangential velocity Vs, okay, times partial C by partial x, which is minus eta by delta x d delta by dx dc by d eta, okay, minus, please make a correction here, this should be Vs, okay, the variation of the surface velocity in the x direction. Okay. Okay. Z times 1 by delta x, okay, and for this z over here, okay, for this z over here I can substitute eta times delta x. Okay. So, I substitute, okay, eta times delta x instead of z over here. Okay. And you can see there is a common factor on the left side, which is, okay, minus eta times dt star by d eta. And I multiply throughout by delta x square by d, so that the coefficient of the right side becomes 1. Okay. Okay. And on the left I will get, okay, Vs delta x d delta x by dx, okay, divided by d. Okay. Okay, so, this is the final expression for the concentration in terms of eta. Okay. And for a similarity solution, okay, this term has to be equal to 1. Okay. has to be a constant, and without loss of generality that constant can be set equal to 1. The solution for C star is obtained by solving this equation. Okay, the solution for C star is obtained by solving this equation. That was the solution that we had just obtained. Okay, that is that C star is equal to 1 minus root of 2 by pi integral 0 to eta d eta prime e power minus eta prime square by 2. That was the solution for the concentration that we had just obtained. What about the solution for the boundary layer thickness? That solution for the boundary layer thickness I will continue in the next lecture. I will complete this part along with an example. Okay, so I will complete this part along with an example in the next lecture before proceeding on to the next topic. So I will continue this in the next lecture. I will see you then.